Chapter 21 is about electric charge, and much of what you'll see here will be a review from previous physics classes. In this slide, you can see electric charge, and an example here is static cling. If you run a comb through your hair, it becomes negatively charged and then can attract these little pieces of tissue paper. And as you recall, charges with the same electrical sign repel each other, and charges with opposite electrical signs attract each other. So here we have a glass rod suspended by a string, and it's positively charged, and you bring close to it another positively charged glass rod, and they will experience an equal and opposite forces in opposite directions. And so if you bring this positive rod close to this one, it will experience a force in this direction, causing it to spin like that. On the other hand, if you bring a negatively charged plastic rod next to this glass rod suspended from a string, they have opposite charges, and so they'll attract, and so the glass rod will kind of swing around this way towards the plastic rod. Here's some definitions. So first of all, we have conductors. Conductors are materials through which charge can move freely. They have conduction electrons. The most common examples are metals. Human body is also a conductor, and tap water because it contains some ions. Non-conductors, also called insulators, and charge cannot move freely. They do not have electrons that can move around. Common examples: rubber is an insulator, plastic, glass, and water that is chemically pure, so deionized water. Semiconductors are somewhere in between. The most common ones are silicon and germanium that are found in computer chips. Superconductors are materials that are perfect conductors, and they allow charge to move without any hindrance. And these properties come about because of the structure and electrical nature of atoms. And then, as a quick review, I'm sure you recall that atoms are made up of protons and neutrons packed together tightly in the nucleus, and negatively charged electrons that are outside the nucleus. And what happens with a conductor is when the atoms come together to form a solid, some of the outermost electrons, and so since they're outermost, they're loosely held, are free to wander about. And so those electrons are called conduction electrons, and they leave behind some positively charged atoms or some positive ions. There are very few free electrons in a non-conductor. Okay, so here we see an example of the motility of electrons in a conductor. So you bring a negatively charged plastic rod next to a neutral copper rod suspended on a string, and this negatively charged rod, you bring it close. The conduction electrons in this copper rod are negative, and so they are repelled from this negatively charged plastic, and so they flee over to this end of the copper rod. Well, when they do that, they leave behind positively charged ions. So now we have unlike charges, and they attract. So this end of the copper rod will be attracted towards the negative charged plastic. Here we have a picture of a wintergreen lifesaver. And if you chomp a wintergreen lifesaver candy in the dark, you'll see blue sparks. This is my understanding of what happens. So when you chomp on it, it breaks. And some of the electrons will be on one piece. And so if they're on this piece, then the corresponding positive ion is on this piece. So the electron, which is then attracted to the positive ion, then jumps from this piece to that piece. Some of them, when they do so, strike a nitrogen atom in the air. When they do that, the nitrogen atom emits ultraviolet light, which is then absorbed by one of the chemicals that makes up the wintergreen flavoring, and then that will then emit the blue light that you see. That's, if I understand correctly, what's going on. Okay, so now we'll talk about Coulombs Law. So this is the main math part of this chapter, and the force of repulsion or attraction is called an electrostatic force. And the equation describing that force is called Coulombs Law. Again, I'm sure you saw this in a previous physics class. And it tells us that the force is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. This r hat right here is just a unit vector that is on the axis between the axis joining the two particles. So here we have an example. We have two positive charges, and so the force pushes the particles apart. Same force on this positive charge as on this positive charge. Here we have two negative charges. Again, same force on each of them, pushing them apart. Here we have a positive and a negative, and so the like charges attract each other, so the force here pulls them together. Now the constant of proportionality in Coulombs law is K. K is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. Another way of writing K is 1 over 4 pi epsilon naught, where epsilon naught is another constant, and it's called the permittivity constant, and epsilon naught is equal to 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. And we'll use both of these, both K and epsilon naught, in our various different problems. So there are a lot of analogies that you can make between the electrostatic force and gravitational force. You have the constant proportionality, you've got the distance squared in the denominator. Here we have the product of the charges, and in gravitation you have the product of the masses. The big difference between electrostatic force and gravity is that gravity is always an attractive force, but the electrostatic force can be either attractive or repulsive. Okay, now just briefly we'll just mention current. We won't be using current for a few chapters. Current is the rate at which charge moves past a point or through a region, and so current I is equal to dq dt, so the rate of change of charge with respect to time. The unit of current is amperes or amps, and dq is the amount of charge moving past a point or through a region in time, dt in seconds. So change in charge over change in time. And so then we can see the definition of a coulomb, and so the coulomb is actually defined in terms of an amp. And so the definition of a coulomb, 1 coulomb is 1 amp times 1 second. 1 coulomb is a huge amount of charge. We usually don't deal with coulombs as more microcoulombs or even smaller. Okay, so if we have n charged particles, then they act independently in pairs. And the force on any one of them, say particle 1, is given by the sum of the forces between particle 1 and 2, particle 1 and 3, particle 1 and 4, particle 1 and 5, and so forth up to particle 1 and n. So if you want to figure out the net force on one particle, you just look pairwise between, let's say particle 1 is here, you look pairwise between this particle and that one, this one and that one, and this one and that one, and then you add them all up as vectors. And so you'll look at some problems using this in a little bit. So F14, when we write it like that, F14 is the force on particle 1 due to particle 4. And so this is a principle of superposition. You can just add them all up to get the net force. A few properties. If you have a shell of uniform charge, so a hollow sphere of uniform charge, it will attract or repel a charged particle that is outside the shell, just as if all the shell's charge were concentrated at its center. Okay, so you can treat it as a point charge. If, however, you have a charged particle inside a shell of uniform charge, there's no net electrostatic force on the particle from the shell. So outside the shell, you can treat it as a point charge. Inside the shell, there's no net force. Okay, you're going to look at some examples in Wiley Plus. So these examples will be worked out for you, so I'm just going to go through them. We're not going to look at them here. You'll look at them as they're worked out. So you'll get to those in a little bit. Now we'll talk about how charge is quantized. So ever since Ben Franklin, who did a lot of work on electricity, we have learned a lot. And so we have learned that, Ben Franklin thought that electricity was some sort of fluid. Now we understand that it's a collection of charged particles. Millikan was one who was able to figure out that this charge was quantized and had to be a multiple of a certain elementary charge that we call E. So E is equal to the magnitude of the charge of one electron. It's 1.602 times 10 to the negative 19. So when we use E, we actually mean 1.602 times 10 to the negative 19 coulombs. If we want it to be negative, we'd have to put a negative E here. The total amount of charge on anything has to be an integer multiple of E. You can't have part of a charge on an electron. And so the total charge has to be either 1E or 2E or 3E, or it could be negative, but it has to be an integer multiple. This E is the charge on both a proton and an electron, so it's positive for a proton and negative for an electron. So here are some of the symbols that we use. The symbol for an electron can either be E or E with a little minus, and its charge is minus E. Notice that's italicized there, or script. The symbol for a proton is P, and its charge is plus E, and the symbol for a neutron is N, and its charge is 0. Okay, so we're saying, when we say that a physical quantity can only have discrete values, so it can't just have any value, then we say that quantity is quantized. So it cannot be any value, it has to be a multiple of some values. So you can have a charge of plus 10E or minus 6E, but you can't have a charge of 3.57E, because that would mean you have a charge of 0.57 electrons. Okay, and then just a little warning here. We talk about charge on a sphere, or charge transferred, or charge carried on the electron. So you might think that charge is a substance, but charge is not really a substance. Charge is a property of particles, and it's just one of many properties such as mass. Okay, so that was a very quick overview of Chapter 21. You're also going to look at some worked out problems in Wiley Plus, and you should do the reading. And I hope you enjoyed it.